So we are now looking at Algebra 2, Chapter 3, Section 1. Now Chapter 3 has to do with all of quadratic solving. We begin by reviewing some stuff from Algebra 1, and then we start to go over some complex numbers, which are the imaginary numbers with the i's, and then we go on from there. But right here, Section 1, this should be complete review from Algebra 1. First off, we have here a quadratic equation in one variable is an equation that can be written in standard form: ax squared plus bx plus c equals 0, and the 0 kind of rolls over to the other page there, where a, b, and c are real numbers and a does not equal 0. And in chapter 2 we had that idea also of a not equaling 0, because if a was 0 then the quadratic term would go away, and then we'd just be left with the bx plus c, which is linear. So that's what this piece right here is saying. Next up, we have a root of an equation is a solution of the equation. We've got a bunch of different words to describe a solution here. A 0 of a function is an x value for which f of x equals 0. So a 0 is an x-intercept. So right here we say often the words root, solution, 0, and x-intercept are interchangeable. Normally these two last words deal more with a graph, whereas the root and solution has more of the connotation of an equation, but all four can be used kind of together. Whenever we solve quadratic equations, we have three ways that we start off by using: by graphing, and we can do that with a graphing calculator, and I'm going to show you all how to do that in class, so that we can do that nice and quick. So I'm going to skip the graphing problems on this notes packet, at least for the video. Next up is to use square roots. That works whenever we have a nice x squared equals 4, or something like x plus 2 squared equals 4. It works out nicely when we just have a big quadratic piece and no linear piece, right? If I had x plus x squared equals 4, then that wouldn't work out. We couldn't do that with just simple square roots. Lastly, we have factoring and using the zero product property, and I'll go through an example of that in just a moment. Zero product property, we'll use that in just a couple moments. Example 1 and example 2 deal with graphing. We'll want to do those in class with a graphing calculator. We could do them by hand, but they end up getting a little ugly sometimes, so we're just going to do it with a graphing calculator. Example 3, we're going to solve using square roots. We can use square roots here because we only have the quadratic term there. There's no linear term, right? The x's are together, right? There's only one spot where there's x's, and the x's are squared. So first off, I solve this problem as if it was 4y minus 31 equals 49. So I'm just going to get that variable piece alone. So I'm going to add the 31 over, and I'm going to get 4x squared equals, I'm thinking that's going to be 70, is that right? 50, 60, 70, 80, no, 80. Now I'm going to divide by 4, and I get x squared equals 20, right? 80 divided by 4 is 20. And then I take my square root, and I get x equals, and when we construct a root, when we take a root, we always have to put a plus or minus in, equals the square root of 20. Now we have to check that we're rationalized, and there are 3 rules about rationalizing. The first rule is that if you can break it apart into like a factor tree and pull something out, we have to do that. And the second 2 rules deal with fractions. There's no fractions in this, so we don't have to worry about that. So we break apart the 20, we break apart them into maybe 4 and 5. The 4 breaks up into a 2 and a 2, so there's a duplicate 2 and then a singleton 5. So our answer here, the 2 comes outside, and then the 5 stays under the root. And we have to put a plus or minus there, of course. So let me write it a little bit nicer. X equals plus or minus 2 root 5. And that's example 3. Scrolling down to example 4, we want to again solve using square roots. This time, our quadratic piece, right? It's not just an x squared, but there's a whole little chunk there. The x plus 3 is squared. Again, I think about solving this as if it was just 2/5 y equals 5, and I try to get my y by himself. So I'd multiply by the reciprocal here. So I'm going to multiply by 5 halves. On the left side, the 5 in the numerator, 5 in the denominator cancel. 2 in the numerator, 2 in the denominator cancel. And I'm left with just x plus 3 quantity squared equals, now on the right side here, over here, I have 5 times 5 gives me 25 in the numerator, and then just 2 in the denominator. Now I'm going to take a square root of both sides because my quadratic piece is alone, and I get x plus 3 equals plus or minus the square root of 25 halves. Now again, in the last problem, I said there were 3 different rules to make sure that a root is rationalized, that it's simplified. The first one is that if you can break them apart, then you have to. So up here we broke them apart. The 20 we broke apart, so we were able to do that, so we did. The last ones, the second 2, deal with fractions. The second rule that we have is that that a radical cannot contain a fraction. So we have a fraction inside the root. That's not okay. So what I can do is I can break them apart, and I can say, well, x plus 3 equals plus or minus square root of 25 on top and square root of 2 on bottom. So now we've taken care of rule number 2. That was meaning that you can't have a fraction inside a root. Now rule number 3 is often the hardest one to finish. It's that you can't have a root in the denominator. Right? These are old rules back from Algebra 1. So what we're going to do here is, well, I'm going to go ahead and just copy it down over here so that I have a little bit more room. X plus 3 equals plus or minus, root 25. We know what that is. The square root of 25 is plain old 5. And the denominator is the square root of 2. Now, to get rid of that square root of 2, we're going to multiply by a fancy 1. A fancy 1, right? The number 1. You can multiply anything by 1. Right, anything at all, but you can multiply by 1, and we get the same thing, right? 5 times 1 is still 5, right? So we didn't change it when we multiplied by 1. And then we know that the number 5 over 5 is also 1. So, right, a fraction where the top and the bottom are the same thing is just a 1, right? It's a fancy one. So here, we're going to choose a fancy 1 over here, and we're going to choose the square root of 2 over the square root of 2. I copied what I had in my denominator there. Now I'm going to have x plus 3 equals plus or minus. Multiplying straight across, I get 5 root 2. And then in my denominator, I have root 2 and root 2. Well, that's root 4. And the square root of 4 is going to be 2. So this is going to be x plus 3 equals plus or minus 5 root 2 over 2. Lastly, I subtract my 3. And I get x equals negative 3 plus or minus 5 root 2 over 2. And that's going to be our final answer. Again, we have these roots, and we have some rules as to what roots have to be in our answer. The first rule is that if you can break it apart, you have to. Right up here, we took the 25. Where would we do that? Right here, the 25, square root of 25 is 5. That's taking care of that first rule. 25 had a perfect square of 5 in it, right? You could say that this is the square root of 5 squared. Square root of 5 squared is 5, which is what we wrote over there. 2 is a prime number, so that rule of breaking it apart doesn't apply to the 2. The second rule is that a radical cannot have a fraction inside of it. So right here, we had a fraction inside of our radical. So we took care of that by breaking it up over the fraction. And then our last rule is that you can't have a radical in the denominator like we did over here. To get rid of that, we multiplied by a fancy 1, right? A fancy 1. And that got rid of the root 2 in the denominator. All right, let's look at our next problem here. Number 5, we're going to solve by factoring. Now this is a little bit of a different method here, right? Whenever we factor, we want them to be equal to 0. Right, and again, this is different because up here we used square roots, and factoring is going to be a different method. Factoring lets you take care of problems that have an x squared and a plain old x. We want them to be equal to 0, so I'm going to subtract the 45. We get x squared minus 4x minus 45 equals 0. Now there's all kinds of methods to factor. Lots of people have different ways. The way that I like to do is I like to first say, well, we have A times C. A is the first number and C is the last one. So A is 1 times negative 45. That's negative 45. Right? And this is just kind of an aside as like scratch work. And now we want two numbers that multiply to be negative 45 and add up to be B, negative 4. Those two numbers for this one is going to be a negative 9 and a positive 5, right? Negative 9 times 5 is negative 45. Negative 9 plus 5 is negative 4. Right? Sometimes it takes a few tries to get those numbers there. Right? You could write down 3 and 15, or how about negative 3 and positive 15? But that does not add up to be negative 4. Right? It doesn't add up to be negative 4. So you would have to try another one. As you do problems more, you normally get quicker at checking or at guessing the two factors, but sometimes it just takes some time. All right, so we have our factors here. That's negative 9 and positive 5. We're now going to break apart the negative 4x into a negative 9x and a positive 5x. So we still have our 1x squared out front. We still have our negative 45 at the end, and he's still equal to 0. Now what we're going to do is factor by grouping. So we have the first two and the last two. On the first two, we look for what could we pull out. We could pull out an x. And then left over would be an x minus 9. Right, and to check ourselves, we could distribute in the x times x is x squared. X times negative 9 is negative 9x. Our second two, we want to factor something out such that we have an x minus 9 in the parentheses again. Right, we want our parentheses to match up. So we look at how could I change my 5x minus 45. How could I turn that into an x minus 9? Well, it would be pulling out a 5. Now we have two bigger terms, this term and this term. They both have the x minus 9 in common. So I pull out the x minus 9, and then my leftover pieces are an x plus 5. Right, there's my x, there's my 5, and this is still equal to 0. Now we do what's called the zero product property. We're going to take, we have two pieces, the x minus 9 and the x plus 5, and they're multiplied together, right? There's like a times symbol in between. When you have two numbers that multiply to equal 0, then both of the numbers separately could equal 0. Right? If you have 2x, well, you know what, let me use a different variable. 2y equals 0, well then y equals 0. So here we're able to say that x minus 9 equals 0 and x plus 5 equals 0. Now these are just plain old linear equations, and we can solve those easily. X equals 9 and x equals negative 5. And we have two answers to this problem. All right, that's example 5. Let's scroll down and look at example 6. This again says to solve by factoring. We already have a 0 equals, so that's kind of nice. Now we're going to look at a times c. A is 1, c is 4, so they multiply to be 4. And we want factors of 4 that add up to be negative 4. That's our b, right? This is a, b, c. Two numbers multiply to be negative 4 and add up to be negative 4. It's going to be negative 2 and negative 2. Negative 2 minus 2 is negative 4. And then negative 2 times negative 2, the double negatives cancel to be a positive 4. So we're going to break it apart here. And we're going to say 0 equals x squared minus 2x minus another 2x and then plus 4. This process on the left just helps us to strategically choose the numbers that we break up the negative 4 to be. Right? If we were to put these back together, we'd get negative 4x. Right? But we're strategically breaking it apart. Now we're going to look at the first two and the last two. We factor the first two, they both have an x, and then we'll have an x minus 2 left over. In the second two, we want to factor something out such that we have an x minus 2 again. Now this time we're going to have to pull out a negative 2. Now they both have an x minus 2 in common, so I can say, well, 0 equals that x minus 2. So I pull it out front, and then left over is this x and then minus 2. And we see there that we have some duplicates, right? They're both x minus 2, which is kind of neat. We split it up and we have x minus 2 equals 0, and then another x minus 2 equals 0. Now, right now, we can just say, well, I only care about one of these because they're going to give me the same answer, right? Both of them say x equals 2. And that's my answer, x equals 2. Later on, as we get farther into Algebra 2, we're going to care more about the fact that there is a duplicate here, right? It occurs twice, so we're going to call that a multiplicity later on in Algebra 2. But that's example 6, and we got x equals 2. For these problems here on our homework, we can have 3 different options. We can have 2 answers, 1 answer, or 0 answers. Right here we have 1 answer. Up top in number 5, we had 2 different answers. In number 4, there's 2 answers, right, because there's a plus or minus. In number 3, there were 2 answers because there was a plus or minus. But they can sometimes have no solution. And that would be if maybe you get a negative under a root. We normally say that's no solution. Now in section 2, we're going to fix that and we're not going to have no solution anymore. But for now, we're still allowed to say no solution. So there we are. That was section 1. And the 2 things that we went over in the video were factoring and then also solving by square roots.